module of digital communication, we have discussed the elements of PCM. In the now coming to the module 4, here we are going to discuss the quantization error, the concept of quantization error, as well as the SNR calculation of PCM system. So before going to the quantization error, first let us see the quantizer. Here you can find the quantization, the process of quantization, whereby the sample signal is taken as input to the quantizer, and this quantizer will divide the amplitude axis into various representation levels. Here it will divide into various representation levels. That is almost all 2 power n number of amplitude levels will be divided for an n-bit PCM. For an n-bit PCM, it will be divided into, if it is like n-bit PCM, 2 power n number of amplitude levels will be available. Okay, now let us assume the input to the quantizer as x of nts, where n into ts represents the sampling interval. If x of nts is taken as input to the quantizer, this quantizer divides into amplitude axis. Divides the amplitude axis into some quantization levels. Those levels are represented as x suffix q of nts, where x suffix q of nts is the output of quantizer having some discretized levels, and input is a sample signal. Now the difference between the output and input of quantization error is called as quantization error. The difference between the output of quantizer and obviously if there is any difference between the output of quantizer and input of quantizer, that is defined as a quantization error. Here, if you see the quantization error, now in the first equation, we have defined the error inherited as the difference between output of quantizer and input of quantizer as E of NTS. Let us assume from the graph you can see that the x-axis represents the input signal, that is a sample signal x of NTS, and the y-axis represents the xq of NTS, where xq of NTS represents the quantization level. It represents the quantization level. Let x of NTS be the input, we already assumed, and it range from minus x max to plus x max. If you assume like this, then the step size delta is defined as the ratio of the total number of the total range, that is x max minus x min, divided by the number of amplitude levels, that is L. So x max minus of minus x max divided by 2 power n is our step size. So you will get 2 into x max by 2 power n. If the signal is normalized, then x max magnitude will be 1. So then delta will be 2 power 2 by L, because if you take x max as 1, then it will be 2 by 2 power n. Now coming to the quantization error. So E max is equal to, here in the plot if you observe that you can find the at any instant, for example if you take when x of NTS is delta, at that respective instant the output is 3 into delta by 2. So error is defined as the difference between output magnitude and input magnitude. So 3 delta by 2 minus delta, so it will be delta by 2. So whatever at any instant the quantization error Emax is equal to mod delta by 2. So that range from minus delta by 2 to plus delta by 2. So finally we should know that the quantization error is a range is from here you can see the range is from minus delta by 2 to plus delta by 2. Now in order to calculate the signal to noise ratio of PCM signal, first we should know the quantization power, that is the denominator. So because SNR is defined as the ratio of signal power to that of noise power. So for calculation of noise power, here you should know the magnitude of quantization noise. Because we are considering the uniform distribution that range from A to B, If it is uniform distribution that range from A to B, then the magnitude will be 1 by B minus A. So similarly, if you consider the error, we know that quantization error of range from minus delta by 2 to plus delta by 2, and it is uniform. So its magnitude will be 1 by B. B is delta by 2 and A is minus delta by 2. So delta by 2 minus of minus delta by 2. So it will be 1 by delta. So here you can see the effects of X as a general expression for the probability distribution function of a uniform response. So it is 0 for x less than or equal to A, as well as for x greater than B, the output is 0. The response is 0. And the response exists only from A to B. So magnitude is 1 by B minus A. So if you apply the same to our quantization noise, Phi of E is a probability distribution function of quantization error, which is equal to 1 by delta, where the error range from minus delta by 2 to plus delta by 2. So beyond that range, the error distribution is 0. Finally, we obtain the quantization noise as the probability distribution function as 1 by delta for error range from minus delta by 2 to plus delta by 2. Now let us calculate the signal to noise ratio of a quantizer, which is defined as normalized signal power to that of normalized noise power. So first let us focus more only on normalized noise power. So normalized noise power is defined as the ratio of mean square value of the quantization noise signal to that of resistance. Under normalization, R can be taken as 1 ohm. So you will get only expectation of error square. So general expression for expectation of x square is integral minus infinite to plus infinite x square into fx of x dx. So the expectation of error square, here we are focusing on quantization error. So it is equal to integral minus infinite to plus infinite e square Phi of E dE. So finally we obtained expectation of error square as integral minus infinite to plus infinite e square into Phi of E into dE, where Phi of E is a probability distribution function that range from minus delta by 2 to plus delta by 2. Here you can see that Phi of E range from minus delta by 2 to plus delta by 2. So please substitute the expression of Phi of E in expectation mean square value of the noise signal. So you will get minus delta by 2 to plus delta by 2 E square into 1 by delta dE. But beyond this range, the distribution is 0. So we have considered only the limits from minus delta by 2 to plus delta by 2. So 1 by delta is it's a constant independent of E. So if you take that outside, you will have integration of E square dE. So it will be E cube by 3 with the limits minus lower limit as minus delta by 2 and upper limit as delta by 2. So expectation of error square is equal to 1 by delta into delta by 2 whole cube by 3 minus of minus, here it becomes positive. So delta by 2 whole cube divided by 3. So here you have delta cube by 8 plus delta cube by 8. So you will be 2 delta cube by 8 into 1 by 3 delta. So finally, upon simplification, you will get mean square value of the quantization error as delta square by 12, because here you have delta cube in the numerator and delta in the denominator gets cancelled, and you will get delta square by 12. So this is the mean square value of the quantization error. Finally, we calculated the expectation of error square divided by R is our quantization noise power. So N is equal to expectation of error square by R, which is equal to expectation of error square by 1 ohm under normalization. So finally, we obtained the denominator as quantization noise power delta as of PCM system as delta square by 12. But in the earlier slide, we have calculated that delta as 2 by 2 power n or 2x max by 2 power n. Just to substitute delta as 2x max by 2 power n whole square divided by 12. So n is equal to 2 into x max whole square. So upon simplification, we will get the normalized signal power as sorry, we will let us assume the normalized signal power as P and the normalized noise power is delta square by 12. Just substitute as delta as 2 into x max by 2 power n whole square divided by 12. So you will get it as 3p into 2 power 2n divided by x square max, where 2 power 2n can be written as L square, where L is the number of amplitude levels decided by the quantizer, where L is equal to 2 power n. So finally, the SNR of PCM quantized PCM signal for under uniform quantization is 3pL square by x square max. So if the input signal x of NTS is normalized, then x max is 1. Just substitute SNR is equal to 3p into 2 power 2n. So it is 3pL square. If you take x max as 1, the simplified expression for SNR as is 3p into L square, where L is 2 power n for an n-bit PCM. If you don't consider x max as 1, then SNR general expression is 3p L square by x square max. If you take p as less than or equal to 1, SNR is 3L square. So here you can see the general expression, and if you want to represent in decibels, 10 log S by N. So here S by N is 3 into 2 power N, considering P as less than or equal to 1. So here in the logarithm, inside the logarithm function, you have 3 into 2 power 2n. So if you write it as log AB, you can write it as log A plus log B. So 10 log 3 plus 10 log 2 power 2n. So 10 log 3 base 10 is 4.77 and 10 log 2 power 2n. This is in the form of log x power y. So you can write it as y log x. So 2n into 10 log 2 base 10. So it is 6.02 n dB. So this above equation, this SNR expression of PCM signal in decibels is called as 6 dB rule, because each additional bit of quantization level increases the SNR by 6 dB. Here SNR for uniform quantized PCM signal is SNR in decibels is approximated as 4.8 plus 6n. For every additional bit of n quantized level increases the SNR by 6 decibels. So this is the SNR expression for uniform quantized PCM signal. Here we have taken one example by taking x of t, we have given with the x of t as am cos omega mt and the amplitude am as 1 volt. Then we have to derive the expression for SNR. So signal to noise ratio is defined, it's expressed as 3pL square by x square max. So P is equal to, we know that amplitude square by R. In the expression of M of t, amplitude is AM. And we need RMS value, knowing the mean. So AM by root 2 whole square divided by R. So it is AM square by 2R is the mean square value of the input signal. And normalized resistance R is 1 ohm. Therefore, you will get the signal power as AM square by 2. So maximum amplitude of x of t is x max if you take it as 1 volt. So upon substituting, P is 1 by 2. So substituting all the expressions in the SNR expression. So we know that SNR expression is 3p L square by x square max. P is AM square by 2 and x is 1. So upon substitution, we will get SNR as 3 into AM. AM is 1 volt. So 1. X max is also 1. So you will get 3 into L square by 2. So this SNR expression in decibels is for the signal AM cos 2 pi FMT with AM 1 volt. So 10 into log 3 L square by 2. So where L is 2 power n. So again upon substitution and splitting it into log x plus log A plus log B form, you will get the approximated as 1.8 plus 6.02 n dB. So this is the SNR for PCM signal with the input message signal as AM cos 2 pi FMT. So that in decibels it is equivalent to 1.8 plus 6.02 n decibels. So similarly here next we have continued with the taking AM as 2 and FM as 250. This we have substituted and obtained the SNR expression, SNR values. And for different types of PCM, here in the first case we have taken L is equal to 128 and L is equal to 256. When L is equal to 128, the number of bits of a PCM grouped per sample in a PCM system is N is equal to 7. So upon substitution, we will get 7.78 plus 6.02 N. So it is almost 49.92. Similarly, we calculated for L is equal to 256 PCM. So here it is a 8-bit PCM. So we calculated and obtained as 55.94. So the higher the value of N, you can observe the signal to noise ratio is more. So the SNR is directly proportional to the number of bits per sample. So in this module, we have discussed the SNR of uniform quantized PCM system. Thank you for listening. In the next module, we can discuss the need for compounding in the module 5. Thank you for listening.